the area under the curve to move from acceleration to velocity and velocity to position information. We already know how to use the slope of position time graphs to get to velocity time and the slope of velocity time graphs to get to acceleration time. And now we want to go the other way. The dilemma we run into is this. If I were to give you these three velocity time graphs and ask you what the acceleration time graph should look like, you'd look at them all and say, oh, they all have the same slope, which means the acceleration is the same for all of them. But that means that if I gave you that acceleration time graph, you might say, well, I don't know which of those goes with it. And that's exactly what we need to figure out. It turns out that you need additional information. If I then said, oh, don't worry, the initial velocity was actually this positive value, you would say, oh, then I can draw this velocity time graph to go with it. But that would only be true if I told you that v initial equals some positive number, because here it's negative for those two. That would allow you to eliminate them. But you do need that extra condition. And so when we're using the area under the curve, we need to do a velocity time graph. From a velocity time graph, we need one extra data point to get that. And that extra data point specifically is the initial position. And for velocity time graphs from an acceleration time graph, you need the initial velocity in order to find that. And so the important things we're going to be looking for here today are the initial condition and the area under the curve. So let's look at how that works. So if I give you an example, here's a velocity time graph with a bunch of different positions on it. I might say, okay, we're going to find the area of this section. We're going to find the area of this section. I'm just doing them in different colors, so it's a little easier to think about them. And then there's also a section in the middle right here. There's not really any area. So three sections we have to worry about. Fortunately, we're given an initial position, positive 10 meters. If the velocity is position over time, change in position over time, then the change in position, this delta x, is equal to velocity times delta t, which is the area here. So the area for our first one is what? That's 4 times 5. So that's 20 meters, and that's positive. So it goes from 10 up to 30 in that 5 seconds. Constant velocity, so it should be a straight line. Then the next segment, we say, oh, there's area equals 0 meters. So that would be a constant position, not changing. We got that right there. And then finally, for our last one, we would have an area equal to negative, so that's what, 5, 10, 15 times 2, so negative 30 meters. So that would drop all the way back down to 0. We would get a line that looks something like that. So we can go and look at that in a little more detail, right? Each of those segments, right? That's the area of the base times height. Connect the dots, keep going, right? We don't have no change, and then we put the last one in. But what if the velocity time graph looks like that instead of the acceleration time graph? This was a velocity time graph that had nice rectangles. What if the velocity time graph doesn't have rectangles? What are we going to do? Well, it's really not any worse. We just need to divide this up into 3 segments. We've got a triangle here. We've got a rectangle here. And we've got, well, that one's a little more annoying, a trapezoid there, right? That should allow us to, using those areas, get up to this. And if I want to go down to here, I know I already just need to use the slope. So what does that look like? Well, to find the slope of each segment, right, we've got 3 different segments here. We've got the first segment, which has a positive slope, the second segment, which has 0 slope, and the final segment, which has a negative slope, allowing us to draw these acceleration time graphs. To go the other way, though, we start with the area of this triangle, and that triangle has an area of positive 20 meters. But we know from experience that if the velocity is not changing, then the slope, if the velocity is changing, it's getting faster and faster, then this line should be getting steeper and steeper. So it's a curve on the position time graph. And it should open up, getting steeper, because we have an acceleration that is positive. The next segment, we have a constant velocity, and this constant velocity here leads to a constant slope position time graph. And then the final segment, which is a trapezoid, which you can either, solve using trapezoid math, which I never remember, or do a rectangle and a triangle and get the final one. So what does this mean? It means that we now have the tools to go using these types of graphs, read directly from it to get position, velocity, or acceleration as appropriate, find the slope of it to get to one more, or find the area, as long as we have an initial condition, to get back up to the top. So that's our big ideas for this video, and we'll see you in class to do some more practice.